Cool. So I'm not really going to be in slides very long. I'm going to be mostly in an IPython notebook showing the code. I'm not going to really talk about theory at all. So there'll be some other talks that'll be good for that. But this is just going to be kind of a quick get you going and a little bit of background to give you context for what's going on. So I'm going to talk about some different levels of abstraction in NuPIC. And that ranges from the lower level pieces of the algorithm and things like the encoders, the spatial pooler, the sequence memory, which is called the temporal pooler in the code, and the CLA classifier, which I'm not really going to cover. And then I'll talk briefly about the networks and regions API, but I'm not really going to go into that, but it's just good to know about. And then I'll talk about some of the different things in what we call the OPF, which is sort of a framework for streaming data models, and there's a few different entry points into that. So I'm going to go through in kind of the order I mentioned them. So first, there's encoders. If you don't know what encoders are, all of the algorithms work on this concept of sparse distributed representations, which is just ones and zeros. And encoders are a way of taking different types of data and turning it into ones and zeros. So we have encoders for scalar values, dates and times, categories, multi-encoders, and there's kind of one main thing that you have to be in mind keep in mind when you create an encoder, and it's just that you want to encode the semantics of the data. So you want similar things to have overlapping bits. So here, this is going to pull up. I'm going to put this online so you guys can all take a look at it after. When you see this question mark at the end, that's just IPython syntax for seeing documentation related to it. So it pulled it up down here. Yeah, go ahead.
The font size a little bigger?
Yeah. I don't know. Is that good? Okay. Cool. So here I'm going to start with a scalar encoder. That's a pretty simple encoder. It basically is going to take a value and is going to encode it in a range that we specify. So here, creating one from 0 to 100, why it's 2.5 and 97.5 instead of 0 and 100 is just an implementation detail for this encoder, but I'm not going to go into. But it's going to create a set of ones and zeros that represents that number, and the idea is that it buckets the numbers over that range and then selects a set of ones that's equal to the W, that's the width of the representation for that value, and then N is the total number of bits in the representation. So again, I'm not really going to go into the theory of SDRs and what this means, but I'm just going to say this is how you get SDRs from values. So here for the scalar encoder, I've encoded a few different values with the encoder that I created. And then there's in the output you can see 4 values that are close to each other that fall into the same bucket. Their representations are going to be the same. So you can see that with 3 and 4. And then when we move into the next bucket above that with the value 5, it shifts the values over. And there's still overlapping bits because the values are close to each other. It retains the semantics of the data. But if you had a much larger value, then it would obviously not have overlap as those values move over. This is a really simple encoder. It's just doing bits right next to each other. And we have, I'll show you, we don't actually use this one currently, but I'll show you another one in a second. So next, I'm going to take a value 100 that's at the very high end of the range, and then another value 1000, which is way outside of the range. And so with this encoder, since it's just representing them between 0 and 100, it's clipping the values that are above the range and just representing them the same as 100. If it's below the range, it'll be the same. So you can see you get the same representations. So we have another encoder that's the random distributed scalar encoder, and the idea of that is that instead of picking these values that slide across the range, it's randomly selecting the bits for each bucket, and that way it can represent a much larger number of buckets. You run the risk of collisions, and so you obviously, if you create enough buckets, eventually you'll have one that's exactly the same as a previous one. But for the purposes of this this demo, I'm going to run this code here. You can see with 3 and 4 they have the same bit representations just like in the previous one, and the 5 is different, but it's not adjacent bits anymore. And then again with 100 and 1,000, 1,000 has a new representation. It's not the same as 100, even though it's outside the range. So that's the random distributed scalar encoder. I'm going to flip through a few more things here. So here's the date encoder.
Good question, Scott.
So Scott, first example, 3 and 4 have the same. The first one, yeah, and
3, 4, 5. That one too.
yeah, and 3 and 4 are the same, yes?
Yeah, yeah. I'm not doing a good job of explaining this. Okay, so here's the takeaway from this. What I'm trying to say, or what I'm trying to show here, is how to use these different encoders and just give you a flavor of the different encoders that ship with NuPIC. So with the scalar encoder, you're taking scalar values and turning them into ones and zeros, and the way that it does this is it buckets the values across that range, and then turns them into ones and zeros. And within a bucket, you're not going to get a different representation. So I think that's what you're commenting on. The 3 and the 4 are the same representation.
Yes.
And that's because obviously we can't represent everything uniquely with this encoder because it has a limited output. And so you have to pick the right N, W, min, max values to make sure that your granularity makes sense for your data. And it can actually be a benefit in some cases because it denoises the data a little bit. So it doesn't have to learn that 4 and 4.001 are the same thing.
So I just recently understood this. So if you change, N here is 22, so there's only 22 slots to have a 1 or a 0. If you change that to 100 and you change your window, the W, to 1, 1 would be the first bit on, 2 would be the second bit on, 3 would be the third bit on. If you changed it to 100 and made the window to be 10, anything between 1 and 10 would be the first bit on. Anything in the 20 range would be the second bit on. So you're just bucketing and encoding scalar values to fit within some of those buckets, how you define the range in the window.
Yeah. Cool. Any other questions about that? Okay, and then what I was kind of butchering, the random distributed scalar encoder, it doesn't have the sequential bits, but it's doing the exact same thing. So until you fall into buckets outside the range.
With the random one, will 3 give me the same representation? Sorry, the word random is confusing. With the random distributed scalar encoder, will I get the exact same representation each time I see a 3?
Yes.
Okay.
Yeah, so I agree the naming is confusing on that. We weren't really sure how exactly to name it. So the random aspect of it is determining which bucket maps to which bits, but once that's done, it's fixed. So.
How many buckets are there?
So in the first example with the regular scalar encoder, there's going to be about 20 because for N and W, the number of possible buckets you can have is with an N of 23 and a W of 3 is 23 minus 3 plus 1, which is 20 buckets. Does that make sense? Because basically that's a bucket, which is represented with these 3 values, and then you shift it over 1 to get the next bucket. So you can fit 20 on this range. And the formula for that is N minus W plus 1. With this example, because we're randomly picking the bits to represent a bucket, you can theoretically create as many as you want. You can keep going. And the problem that you run into is collisions with values. Here I'm showing very small numbers. So an N of 21 and a W of 3 is not a very good representation in most cases because you're going to have a higher risk of collisions since you only have 21 bits, and it's not going to deal with noise or collisions very well because you only have 3 active bits. If you, yeah.
Since you can have a lot more of them, then why are 3 and 4 the same still here?
Matt, do I need to repeat this?
Yes.
Okay, so the question.
Hold on.
So in this example, because the 1s and 0s can be anywhere along the range, why should 3 and 4 be the same?
Okay, that's a great question. So, this is a scalar encoder. It's not just integers. So you can get a floating value as well, a floating point value as well. So you don't want it to represent every single thing it sees uniquely because things that are different by 1/1,000,000th of like a 0.0001, you want that to be treated the same in most cases. But it's different by data set, so you have some flexibility over that. I'm setting the resolution, which tells it how big to make a bucket, and then an offset as well. So it's basically going to make each bucket 5 wide.
So if you set that to 1, each of those integers would be unique.
Yeah, actually, I can do that. We can see. Yeah. So here, I think they're getting. So yeah, they have 2. 3 and 4 have 2 shared, and then 1 different because it's the next bucket, and then 5 drops another bit and adds another. So it shares 5 shares 2 with 2 bits with 4 and 1 with 3.
So that means the window is just the number of bits that are on for any given number, not the size of the buckets, because that's what the resolution is.
W?
Yeah, W.
Yeah.
Okay.
It's the number of active bits. Okay, so those are scalar encoders. I'm going to show you 2 other kinds. One is the date encoder, and the date encoder it encodes in different ways. You have options for how you want to encode a date. I'm not going to go through the documentation. So in the example that I have here, I'm going to encode a date as I'm going to encode the season of the date. When you create a date encoder, you can tell it what you want to use from the date to encode. So you can choose season, you can choose day of the week, you can choose weekend versus weekday, which is just a Boolean. And then it's going to capture that aspect of the date in the output SDR. So in the example here with season, the value 5 is essentially the W that we had in the scalar encoder, but specifically encoding the season. So I'm creating 3 different date times and encoding them. One is right now, roughly. I guess it's a little bit later than that now, but I was guessing what time I'd get to this part of the talk. And then next month, and then I just picked another time, Christmas. And what you can see in the output here is for each of these encodings, you have 5 active bits because I specified that in the construction of the encoder. And it's capturing the seasonality. So it's selecting the total number of bits to represent the whole year. So since I said I wanted 5 active bits, it wants, I think it's, I'm not actually sure how it's picking the total number of bits. It's basically, I guess, making 12 buckets roughly. But you can see if I take now versus next month, there's some overlap between them, these 3 bits, and some difference between them. Where when I encode Christmas, you get the 3 at the end here and the 2 at the beginning, and that has no overlap with now and next month. And so that's how it captures the semantics of seasonality, which is that it's doing it roughly. That's how you capture the seasonality of it. So days that are in the same season should have some overlap, and if you fall like on the opposite ends of the year, you're not going to have any overlap. So that's the day encoder. Like I said, there's a number of different options for that, like weekend versus weekday, day of the week, things like that. I'm just doing season here, but you can do whatever makes sense for your data. And you might ask, how do you know what works well for your data? I'll talk about that towards the end with swarming, which is a way of selecting parameters for your data set. Okay, one more encoder before I move on is the category encoder, and that is a similar idea. I'm going to just pick 4 different values as categories and specify them in the constructor to this category encoder. I'm going to say a W of 1 or a 3, which again means 3 active bits, and then I'm going to code each of them and print them out. So basically what this is doing is it's picking 3 bits for each of these categories and having no overlap at all. Because they're categories, there's no way for it to not know any semantic similarity between them. Then you'll notice there's also these first 3 bits that aren't active for any of the 4 categories that I specified. You might think that's if there's a none value, but it's actually if you get something that's not none, but also not one of your categories. So that's a category encoder, and I'm going to actually use these 4 SDRs in a second to show how the spatial pooler works. So that's encoders. I'm going to move on to the spatial pooler unless anyone has questions about.
For the category encoder, it sounds like you can't store because it's kind of a design constraint, you don't want overlap, so can you not do as many categories with a given set of bits as you can do other things?
Yeah. So that's a good question. So you're saying with the same number of bits?
Correct.
Yeah, okay. I don't really know how to answer that. So I guess you can represent a much larger number of integers when you're bucketing them, because you can have the same number of buckets as categories here. Actually, you can have more buckets because you have overlap between them. I see. So yes.
Interesting.
Yeah. And it also brings up a good point. Do you need to have totally exclusive bits for a category encoder? And you don't need to. You could do something similar to the random distributed scalar encoder, where you randomly pick the bits, and then just hope you don't have collisions very often. And if you picked a large enough NNW, like maybe 300-400 bits total and 30 or 40 active, that probably would work just fine.
I think we actually have a category encoder like that.
And we actually have a category encoder just like that. Cool. So next is the spatial pooler. Again, I'm not going to really talk theory here, but the spatial pooler takes 1s and 0s as input, and it outputs a sparse set of 1s and 0s that hopefully captures the spatial invariance of the input pattern. So it's going to adjust itself over time to represent the input space well. So it's sort of a transform from all possible inputs into the sort of most common groupings, if that makes sense. And actually, there was a paper that I was going to put a link to in here, but I forgot. Someone had put a paper up on the mailing list comparing the spatial pooler to clustering algorithms. I thought that was an interesting use of it, an interesting comparison. But so again, there's the documentation. So if you guys pull this up, you can go through this and run these examples. And I just put this line in, so it's easy to get to the documentation if you want to look at that, or if I needed to look at it based on a question from you guys. But don't know why I have all these. Okay, so what I'm going to do to show how to use the spatial pooler is I'm going to have it learn the 4 categories that we created with the category encoder. So first, I'm just printing out the length of the output from the category encoder for cat. So it's 15 bits long, and we're going to use that when we construct the spatial pooler to tell it how many input, how big the input is. Input dimensions, that can be multi-dimensional. So if you're doing a vision problem, you can do 2-dimensional data. Here I'm just doing 1 dimension, just to show how it works. I'm going to give it 4 columns, and the reason I'm going to do that is because we have 4 categories, and I'm going to try to have the spatial pooler learn to represent those 4 categories well, or exactly learn those 4 categories. In a real situation, you probably want a lot bigger numbers than these, and you don't necessarily need, you would not want a 1-to-1 mapping between columns and categories as I'm doing in this example, but I'll talk about that more after I show this. So there's a few other parameters here. Potential radius says of all the input bits, how, for a given column, how many of them can it potentially connect to. And in this case, I'm going to allow them all to connect to any of the input bits, and I'm setting global inhibition to true. I don't really know how to explain this without getting into a lot of detail, but let's say in a vision problem, we're doing a 2D topology, so you have a 2-dimensional input, and what you can do in that case is you can lay out the columns in a similar way so that the column in the upper left corner can only connect to the input bits in the upper left corner. And that way, different columns can learn different local features. And then if you had temporal pooling, you could use a hierarchy and learn higher level things as you move up, things like that. In this case, I'm just going to do totally flat space. All the columns can see all the input bits. And the inhibition is global. So rather than columns inhibiting other columns next to them, or next to them, they inhibit all of the columns, which means that out of the total pool of columns, we're going to limit the number that can be active globally to 1 in this case, because I'm setting that here. Another couple parameters for increments. And then I'm going to just create a numpy array, and that's going to capture the output. So when you're using the spatial pooler by itself, the way that it works is you call, where am I? You get, oh, what did I just realized? Oh, I see, okay. I lost track of where I was. Before I feed any data into the spatial pooler, I'm just going to print out what columns or what input bits each of the columns are connected to, and that's randomly initialized. So each of these vectors is, each of these bits match the input bits that come in, and a 1 means that the column is currently connected to that input bit, which will make more sense in a second. But the point of showing this is that they're random initially. And when I feed data in, those are going to adjust. So some of the columns, like one of the columns is going to learn to represent one of the categories, another one is going to learn to represent another one, and you'll see what that looks like in a second. So here I'm going to feed in our category cat and look at the output from the spatial pooler. So sp.compute, the compute method is how you do that, is how you feed data into the spatial pooler. And that's going to put the active columns into this active array. And the way it selects the active columns is by having each of the columns look at its connected bits and sum the ones that are active in the input. And then they compete. So the ones that have the most active in their connected pool will win. And then with learning set to true, it'll increase the connected weight, the weight of the connection to that input bit for all the ones that are active, and for all the ones that are not active, it'll decrement them. And the implication of that is over time, the inputs that a column is active for, it'll learn to represent those better. And so where we start out with random connections here, after I feed in the value for cat 20 times, if I print these out again, you'll see that this third column, which was the one that was active for it, which is this one here, has adjusted its connected weights so that rather than being connected to a random set of these input bits, it's now connected to the ones for the input that it's active for most commonly. So again, when we look at these random connections and we feed the value for cat in, the active bits in cat are these three. And so all these columns competed to become active, and this third one was the one that happened to win. And that's because it had connections to all three of those bits. You can see the second one did too, so there's a little bit of randomness there. But the third one won, and so then when I fed cat in a whole bunch of times, it would adjust its weights. These three connections would get incremented, so those would stay connected, and these other ones that are active got decremented. So when I printed the weights out again after feeding cat in a whole bunch of times, those, the ones that were active that are not in the input got decremented and are no longer connected. I hope that makes sense. I'm kind of not explaining that well. Okay, so the next thing I'm going to do is I'm going to feed in all four of the categories that we created. And I'm going to do that 20 times so that the weights have a chance to adjust, and then we'll look at the output, or we'll look at what input bits each of the four columns are connected to. So I'm going to run that, and then I'm going to go do this loop to print out each of the columns again. Now you can see that the columns have adjusted their weights, so rather than the random connections that we had up here, the third one, like we saw before, is connected to all the bits for cat. This fourth one is connected to all of the input bits for dog. And then we see something interesting here. We have a column that represents monkey perfectly. It has the three monkey bits on and none of the others. We have one that also partly represents that. And then the column that represents cat started to also represent the slow loris. I guess it's not obvious which of these is which animal, but I just happen to remember from before. Why is that? Well, again, these columns are competing for these values, and so what you can have happen is one value, or one column may become active it may win for multiple animals, and then it's going to be incrementing its weights for the bits for monkey, or for cat when it's active for cat, and decrementing the other ones. But then when slow loris comes and it happens to win for that one, it's going to increment the value, the connections to the slow loris bits and decrement those for cat. So it just happened that this one learned to represent two different things, even though there was another column that maybe could have. And we can keep running this a whole bunch, or we can keep running this a whole bunch and see if they end up evening out. But it looks like this is maybe the steady state for this. I don't think that's going to change. So I was expecting that each column would represent one of them perfectly, but it turns out that that's not what happened in this. But
could you potentially tweak the parameters and then get them to represent?
Yeah, there's always going to be some randomness. I was trying to explain how that could happen, where one happens to win for two different animals, and then you have another column that doesn't really represent anything, or maybe partly represents one of the animals. And what you'll see in a real system is generally, I was trying to say this at the beginning, normally you wouldn't want to try to do this one-to-one mapping. You just have a big pool of columns and a big pool of inputs, and some columns will learn to represent specific parts of an animal. So this is really simple data, but you may have one column that represents the first 2 bits for an animal and another one that represents the third. In real cases, you'll allow multiple columns to be active at the same time, so you can get these much more complex representations where you have some of these features and some of these features.
Hold on.
Would you have better results if you don't inhibit globally? With this specific example.
Yeah, that's a good point. So in this example, probably, because we could have, if we knew that this is what we were doing, we could set it up so that the columns could only potentially connect to 3 bits. Like we could have 5 columns, say that their radius is 3 bits, and not have global inhibition.
Okay. But that's supposing that we know all the categories from the beginning, and we know.
Yeah. So we happen to know that in this example, and I don't know if that's necessarily a property of global inhibition. Topology here, like taking advantage of the topology, would be useful because we know how the bits are laid out. But in more complex cases where the input is not laid out evenly, that might not help. In a vision example where you have 2D input, it's very obvious and very intuitive that you would lay the columns out 2D as well and have a local field that it can look at. In other cases, like in our product Grok, where we have streaming data and a timestamp, you can have multiple fields. That's a little more confusing how topology would help. So we use global inhibition normally, but you don't have to.
Thank you.
So I'm not going to go too much into the properties of the spatial pooler. I'm mainly just trying to show how to use these different pieces, but I want to show one property, which is the spatial invariance that it learns. So I'm going to create a new SDR that looks like cat, but is a little bit different. So I'm taking one of the bits, 3, which is counting by 0, so it's the 4th bit. And remember, cat is the 4th, 5th, and 6th bits. So I'm going to take the first of those and I'm going to take the first 2 of those and set them to 1, so it represents most of cat. And then I'm going to pick another bit that isn't part of cat. It happens to be part of dog. So let me print that out real quick. So normally, if I had an SDR for cat, like if I use the category encoder, if I had cat in, I'd get these 3 bits as 1s and all the rest 0s. But I'm just artificially creating an SDR that's a little bit different. It mostly looks like cat, but it has 1 bit from dog. Now if I feed this into the spatial pooler, what should happen? Well, the columns are going to be competing to win out. So we can look at our connected synapses here, and we can see this 3rd column is going to match 2 out of the 3 bits, and the 4th column is going to match 1. So I expect that the 3rd one will win. It'll have the most overlap, and so it'll win, and it will basically say it'll see that input pattern, or the output pattern will be the same as if we had fed cat in. So this is essentially what the spatial pooler is doing. It takes noisy input and outputs a stable representation of it, an invariant representation of it. So the output is going to look like this, which is basically going to be the 4 columns and which one's active. So when we did cat before, it was this 3rd column that was active because that's the one that's connected most to it. And we expect that we'll get the same thing here. So let's run this. And yeah, we do see that. So the 3rd column, which is the one that represents cat, is the one that's active. So does that make sense? Everyone get that? Yeah. I can repeat it, man.
Since cat's pattern has 6 bits of 1s, those 3 from the other category that it matched, I forgot what the animal was. It was something unfamiliar to me. The loris.
Yeah, that's the loris.
The cat pattern matched both the cat and the loris.
Mm-hmm.
So when it tried to match the noisy cat, 2 out of 6 bits, only 2 out of 6 bits matched.
Yeah.
So how does that compare with the dog pattern, which matched 1 out of 3 bits?
Yeah. So it's going to look at the sum of its connected bits that are active, and that's what it uses when it competes with the other cells. So the biological analogy would be the neuron. So it's going to sum the inputs on a segment of a dendrite segment, and it's going to get it's going to either fire or not, and whoever fires first can inhibit its neighbors. So even if you have way more segments and synapses on you, it doesn't matter if those ones don't matter, just the ones that are active that matter.
Okay, thank you.
And again, it's going to, when cat is active, it's going to strengthen its connections to the input bits that are active and weaken the connections to the ones that are not active. So it's going to weaken its connection to the slow loris in that iteration. But then if it sees slow loris again in the future and becomes active, it'll strengthen it. And generally, the amount that we increment the connections is higher than the amount that we decrement it. And that usually works out well. Okay, so that's all I have for the spatial pooler. I'm not really going to go into too many of the properties of it. There'll be some other talks on, I don't know if there'll be a talk on spatial pooler theory, but there's plenty of information online, videos, and talks by Jeff and other resources. So any questions about using the spatial pooler?
Sorry, like when you set the learn equal to false, isn't that where it increments and decrements? Or
Oh, yeah.
so it's false right now? Okay.
Yes, okay. So with learning set to false, it's not going to change the weights. Yeah, I didn't realize I had set that to false there. But good point. So you can enable and disable learning as you want. Generally, you leave it enabled. I'm not sure why I decided to turn it to false here. But, yeah.
Because Snowden.
Yes, sure. Okay, so the last individual piece I'm going to talk about before I talk about some of the higher level ways to interface with the code is the sequence memory, which is called the temporal pooler in the code. And the temporal pooling is where, or the sequence memory is where it learns the patterns in the data over time. Generally, you take the output from the spatial pooler and feed it into the temporal pooler. You can also use the temporal pooler by itself. In Chaitin's linguist example earlier, that's using I believe it's using the temporal pooler just by itself, and it's feeding the word SDRs from SEP's API directly into the temporal pooler. And then it's looking at which columns are active, and it's mapping the columns one-to-one with the bits from the word SDR, so it uses which columns are predicted to know what word is predicted. It uses those bits and feeds it back to the SEPT API. So this is an example I pulled from the hello TP script in the code. That's just a simple demo that I think Subutai created. And so this is in NuPIC in examples TP hello_TP, so you can find it there. But I'm just going to walk through it real quick. Here I'm creating an instance of the TP. I'm not going to go through the different parameters, but you can say how many columns you want, how fast to learn by, like how much you increase the permanences of the connections, different things like that. Once you have an instance of the TP, you need some data. So I'm just creating, this demo just creates fake data to feed in. And then to send the data in, you call the compute function. And actually that's the same as SP. In this case, you feed it the array that you want it, the input array. Again, you can enable or disable learning. And then That's not important. So I'm going to feed these arrays in, and I'm not getting the output here or doing anything with it yet. I'm just learning the sequence initially. And then I'm using a reset in between each of these loops. And what that does is, yes, Matt?
I'm wondering about the input to the temporal pooler. Is the output of the compute function from the spatial pooler directly the input for the compute function of the temporal pooler?
If you're using the CLA model or the OPF client, you have a spatial pooler and a temporal pooler in your network, then yes. In this example, I'm creating artificial data to feed into the temporal pooler. I'm not using the spatial pooler that I created before. I'm not using the outputs from that.
Right.
Yeah, does that answer?
Yes, thanks.
Okay, okay, so I'm gonna run this. The reset here allows you to learn a sequence, and then if you have multiple sequences and you don't want to learn over that boundary, you can put a reset in between, and that stops it from learning a transition from the end of one sequence to the start of another. Later on, when I do the CLA model, I'm going to use the hot gym example, and in some of the hot gym data sets, it's just one of the data sets, ignore the name. But it's a data set of electricity usage in gyms, and they have different locations. And so if you were training a model on that data, you'd want to put a reset in between the sequence from one gym and then the sequence from the next. So you're not like learning over that boundary. Okay, so now I'm going to send the same sequences in, and we're going to look at the predictions made by the temporal pooler, and they should be accurate now because I don't have any noise in this data. It's very clean, simple to learn, and I fed it in a whole bunch of times already, so it should have had time to learn the sequences. And then there's this function that just prints out the SCRs that are predicted and the ones that I'm feeding in, so you can see what it looks like. All right. If you're doing this yourself, you can see here there's this TP print states. So when you call the compute function on this, you pass the array in. And then if you want to get the predicted cells, then you can get them with the get predicted state here. And then I'm just going to format those in a way that makes it easy to read them. So I'm going to run this, and the output of this is it's basically going to, for each input vector, it's going to print it out, so you can see that here. And then it feeds it in, or it looks at the predicted state, what it's predicting is going to happen next after feeding that record in, and I'm printing that out, and then we can go to the next input and see that. So basically what we're seeing here is I feed this raw vector in, the active state inside the temporal pooler matches the input because those columns become active. It makes a prediction based on the connections of the cells and what it's learned in the past, and predicts that this next set of bits are going to be or this next set of cells are going to be active. And then we feed the next record in, and since it's already learned this sequence, it is correct. And so then we see that those columns are active, and then it predicts the next value. So this all matches. I'll let you guys can look at this later for more details. One important part of this is that in the temporal pooler, it's learning these sequences in context. So when we created this temporal pooler, we said we picked a number of cells per column and set that to 2. And the cells inside of a column all represent the same spatial pattern, but in different contexts. So when we see the output of this, the top row is one cell, and the bottom row is another cell. So this is one cell in the first column, and this is the second cell in the first column. There's just 2 cells. And so when we see a value like this B, this is in context. So because it was predicted as coming from A to B, these cells not only represent the spatial pattern of B, but it represents it in the context of coming from A, from this previous sequence. And that's, so if you were, you can go back and look at this example and try putting letters in different orders and see how you'll get the different, for a given spatial value, you'll always get the same columns active, but you'll get different cells depending on the context. Okay, so that's pretty much it for using the temporal pooler. Again, you can look at the example here and the parameters. The parameters aren't always fully explained, so feel free to grab me if you're trying to use this and you don't understand what the parameters are. The best way to start with this is to find an existing example with data that's similar to yours, and then just start with those parameters. I guess I should go to, and then once you have your temporal pooler, you call the compute function, pass the array in to get the predicted cells. You call the get predicted columns, or get predicted state to get the predicted cells out of the temporal pooler. So that's pretty
Let me
much
just
it.
say that's really useful if you end up working with sept word SDRs and you want to get the next predicted word, you'll call the TP's get predicted state and turn that into a word SDR bitmap to send to sept API and ask it what is the closest word to this SDR.
Yeah, and these are really simple examples with really small numbers, so it's easy to visualize. Like 2 cells per column is pretty small. Typically, in the examples you'll see we use 32, which is probably more than we normally need, but it's big enough that we'd never have problems with it. And the linguist example is, or the fluent example, is probably a good place to look for a more complex use of the temporal pooler rather than a simple dummy version like this. Any other questions about the temporal pooler? Okay. I'm going to switch back to this. So I've covered the algorithms. Don't worry, the rest of this is going to go hopefully a little bit faster. There's not too much more. But I'm not going to show examples of using the networks and regions API, but I kind of wanted to just mention it to give you an idea of what it is. What I'm trying to capture in this slide is that there's different levels that you can access the code at. So all the stuff I just showed was using the algorithm implementations directly, just instantiating the SP, instantiating the TP, and feeding data in and getting the data out. There's some ways to use those that I'll talk about in a little bit that are a little bit higher level, where you can just sort of specify the parameters and where your data is and then just run it. And that can be really useful, but it's sometimes a little hard to understand what's going on. So the networks and regions API is sort of intended for arbitrary topologies of the different pieces. So you may want to have, well, here I can show you an example. So here's an example of how you may set up a topology. You may have 2 different inputs, audio and images, and so you'd want, at the bottom level, you want the encoders for those. So you create some encoder for audio, some encoder for an image, and then you'd have the output of those encoders go into a spatial pooler to learn the spatial invariances, and then the output of that go into a temporal pooler to learn the sequences over time. And then you can have the outputs of those temporal poolers combine into a single spatial pooler. And then you can put another temporal pooler on top of that to learn transitions over that higher level output that you're going to get from the spatial pooler of the combined inputs. And then you can put a classifier at the top to say what's happening in the images or in audio or whatever your problem is. But what the networks and regions API is really nice for is that once you set this up, you feed the data in to it, and it propagates it through all the different pieces, and then you can get the output. So you don't have to manually create all these different pieces, feed it. your audio into the audio encoder, take the output of that, feed it into the spatial pooler, take the output of that, feed it into the temporal pooler, et cetera. The network, you just call, I think, the run method on it, and it does the whole thing. It also formalizes serialization, so each of the regions can decide how it wants to serialize itself, but then the network will call into each of those functions to serialize them and store them with a file that knows the topology of the network. So it's pretty useful for experimenting with this type of stuff. Like I said, I'm not going to show examples of that, but what I am going to show next is the CLA model, which is part of the online prediction framework, and that has a network inside of it. And that network is configurable, so you can say whether or not you want a temporal pooler, for instance, in your CLA model, and it'll create the region for that in the network for you. And so when you feed, I'll show you, so when I show you feeding data into the CLA model in a little bit, that in turn feeds it into a network internally. I mentioned a little bit when we say online prediction framework or OPF. It's kind of a set of tools for running streaming data sets. It has sort of a pluggable architecture for different types of models and different metrics for evaluating models or comparing them, and then some related tools. So one of the pieces is the CLA model, which is generally is kind of an encapsulation of all the pieces that I showed before. So rather than creating those yourselves or using the Networks and Regions API, the CLA model kind of encapsulates the most common case that we have, which is a single level of encoder, spatial pooler, optional temporal pooler, and then a classifier, which turns the output of the temporal pooler, the predicted cells, into a predicted value. I also didn't talk about the CLA classifier or show examples of that, but maybe I'll send out a follow-up with information on that. Okay, so let's run through this example real quick. This is, again, just copying an example in NuPIC, so you can find that in here, and it's doing mostly the same thing as that file. So the way that you create a model is with the model factory, and you pass in params here. We haven't defined it yet, so I'm going to show you what that looks like. I'm not going to go through all of these, but the model tells it what type of model that it wants. Again, the OPF, it's got this pluggable model system, so it knows that CLA maps to the CLA model. There's some other information we're not really doing. It supports aggregation, so here we're aggregating hourly. The model params are what actually go to the model. So we're using a CLA model, so it has some different parameters, one of which is the inference type. In this case, I'm going to do temporal multi-step. There's also a non-temporal multi-step, and that is if you don't want to use the temporal pooler. And that sometimes works better if you have data that can be predicted on with just a first-order model. Okay, so I'm not going to go through all these parameters, but I wanted to put them in here just so you could see what they were. These control things like how fast the model learns, for the encoders, what N and W to use, things like that. Here, this isn't, some of the tools in NuPIC make it easy to get data sets and experiment. So there's this function find data set, and that has a few different rules. You can set an environment variable to have your own directory that you have your data sets in, and then you can use this function just to get the full path for a file based on the different rules. So first, I just wanted to show what this data looks like. So I'm just opening it up and printing out the first few lines. This is a file format that our tooling understands. So there's a file reader that understands this format, and it has 3 header lines and then the data. and it's a CSV format, but it's going to take these first lines and use it to understand the data. So the first one is just the names of the fields. The second one is the type, and that makes it easier to work with datetimes and floats and things like that. And then there's a few other options here. This S means that it's a sequence. So I mentioned earlier how in the hot gym data set there's different gyms. So this first field is the gym that it belongs to, and this sequence flag, or when you put an S in here, it's the sequence flag, and that's basically going to insert a reset when that value changes. So when we get from the ball, whatever, I don't know how to pronounce that, but when we get from that gym to the next one, it'll insert a reset so it doesn't learn over that boundary. But then we have an address, a date time, and then the scalar value. And we're not going to use all these fields in our model. We're just going to use the date time and the value. And that was controlled by our encoders, which are set up here. So here we're doing the time of day and the consumption, which is the value that we want to predict. Cool. So here I'm using another piece of the tool chest, which is the file record stream. It understands that file format. So when we open it and print out the data, it's already stripped off those first 3 lines, and it interprets the data as the appropriate type. So it, rather than a CSV reader, which would get this as a string, it understands that it's a float, and it parses the date time. And this isn't really that important, but I want to include a few of the pieces so that when you're working with this, you don't have to reinvent the wheel. Or if you're working with our data sets or see this stuff, you'll understand what it's doing. So now that we have our model parameters, we can create the model again, and then when you're doing prediction, you have to tell the model itself what field we want to predict. So we're going to tell it here that we want to predict consumption. Once we have that model, we can feed data into it, and I'm going to feed 100 records into this, and I'm going to print out the input, which is the consumption field in the record that you feed in, and then I'm also going to print out the inferences that I get out of the model. So before I do that, just really quickly, the way that you feed data in is you call the run method, and it takes a dictionary where the keys are the names of the fields and then the values are the values. So that's what I'm doing up here when I get the data from the file reader. It's just giving me the values, and so I can get I think there might be a helper function to do this, but I'm kind of zipping it together myself where I get the field names and the data, and that turns it into a dictionary, and I can show what that looks like. If I run this really quick, this is what the full record looks like. But again, we're only specifying encoders for 2 of these fields, which is the date time and the consumption. So the address and the gym aren't actually going to be used in the model. Okay, so I'm going to feed a bunch of records into this and print the results so you guys can see what that looks like. So here I fed in value 5.3. Initially, the model doesn't know anything about the data, so it doesn't know what to predict. It just predicts the value it just saw. But if we run this enough times, the model will start to learn the data and get better at predicting it. And so I'm just going to do this a few more times so it looks like, yeah, now it looks like it's gotten, I've run it through maybe 6 times the 100 records, and you can start to see how it's making a prediction about the value dropping. It starts during the day, the consumption is higher, and overnight it's lower. And so you can see that it's making this prediction of a value of 1 point something when the value is still pretty high. But it's because it's learned the data now, it knows it's about to drop down to a lower value. So that's the CLA model. One thing I didn't mention when we were looking at the parameters before was there's a field for saying how many steps you want to predict, and I had set that to 1 and 5. So what I was printing out here was the best prediction for a single step into the future, and that's what we're seeing here. And I'm not going to print out a whole 100 records, but I just wanted to show that you can get, you can't quite see this, you can get the 5th step prediction as well, which is here. There's actually quite a bit more information that you get when you run a record through a model. I kind of wanted to show the simple version first. And so I'm going to come back to that in a second and show the rest of the information that you get in this result from the model. But first, I wanted to show another type of model, which is an anomaly model. And so in addition to getting predictions out, you can also get anomaly scores, and that tells you how unusual the data is. Essentially what it does is looks at the predicted and active cells in the temporal pooler, and the proportion of active cells that were not predicted, or the percentage of fraction of active cells that are not predicted, is the anomaly score. So if most of your cells that are active were not predicted, your anomaly score is going to be above 0.5, and if most are not, and most of them were predicted, then it'll be under 0.5. Does that make sense? Okay. So here I just put the model params again. These are identical. There's 2 differences, I think. One is that I've changed the inference type from temporal multi-step to temporal anomaly, and that tells it that we want to get the anomaly scores out. And then down at the bottom, there's this anomaly param section, although I don't think that's really doing anything. I don't think you need to include that. So I'm going to run through the example I did before. Again, same thing, create a model with the model parameters, specify the field that we're trying to predict, run some data through, and print it out. Here's the predictions, just like before. With an anomaly model, you still get predictions. It's still doing that. But you also get this anomaly score. I'll show that first. Oops. Oh, I know I didn't do that. Okay, so here if I print out, rather than printing out multi-step best predictions from the result inferences, I print out the anomaly score, and I get a value here. I recreated a new model to do the temporal anomaly rather than temporal multi-step, and because of that, I didn't have any of the learning from before, so it's completely new model, doesn't know anything about the data. So I fed 5 records through, and so that's why the anomaly score is a little over 0.5. Most of the columns were not predicted because it hasn't learned the data yet. So I mentioned I'd show you more of what's in the model result. So here I print out the whole result, and this isn't a very pretty format, but I'll point out the important parts. So here the inferences section is what we are using. We are using multi-step best predictions for the predictions, and the anomaly score, where is it? Here. There's also we're using the multi-step best predictions, sorry. Multi-step best predictions, for each step that you're predicting, it has a single value, which is the best prediction, and it's the predicted value. In multi-step predictions, you actually get multiple predictions. So for one step, we have this dictionary that maps from the value that's being predicted to the likelihood. So this is saying there's a 23% chance of the next value, the value one step in the future being 5.1, and a much higher chance, 76% chance, that it'll be 5.34. So there's a lot of information in this result set just in this inferences section. So that includes multiple predictions for each step into the future that you've specified that you want to predict, the anomaly score if it's an anomaly model, and then in addition to the inferences, this record includes just the raw input that you fed into it, as well as some process things like data encodings, which is the raw input after it's been encoded with the encoders that you specified, and some other things like sequence reset. So if we were using that sequence field with the gem name, this would be you could see when we cross the boundary because it would show sequence reset as 1 here. Cool. So again, the inferences section here is really what you're generally going to be using. The rest of the stuff is to understand a little bit more detail what's going on internally. Are there any questions about that?
So the model, is it using only the temporal pooler to determine all this, or does it do any extra work that's not available in the temporal pooler to do the anomaly detection or the predictions? Yeah,
so in both of the examples, I specified temporal multi-step and then temporal anomaly. So in both and then in the model parameters, you can also say enable or disable the temporal pooler. But in both these examples, we're using encoders. We're using a scalar encoder for the consumption value, which is the predicted field. We're using the date encoder for the date time, and I think it was doing day of week is how it was encoding the date. So we're using the encoders, and then the output of that is feeding into a spatial pooler, and then it's feeding the output of that into the temporal pooler. And there's also a CLA classifier on top, and the classifier takes the output of the temporal pooler and tries to convert the predicted cells back into a value. So we're predicting a scalar field, so it'll know that some cells are predicted, and its job is to figure out what is a scalar value to call that. And that's where it figures out multiple possibilities and how likely it thinks they are. So for the anomaly detection portion itself, the anomaly score is computed solely based on the state inside the temporal pooler, but you're still using all those other pieces. With the exception of the classifier, you don't need the classifier for that. The reason why we still have the classifier, though, is we do swarming a lot, which I'll describe in a little bit, and swarming is used to figure out what parameters are best for this data set, and without the classifier, there's no way to evaluate how good the model is. If you basically have to use the prediction to see how good the model is, and then we use that to pick the best parameters. But once you've picked the best parameters and created the model, if you just want the anomaly score, you don't need the classifier. Okay. Okay, so that's it for this notebook. I'm just going to show a few command line things. So the CLA model, like I just showed, can be created programmatically. You can feed your data in and get the results out and do whatever you want with them. We have a few tools to make experimenting with these a little bit easier. So one of them is this OPF run, one of them is this OPF run experiment script, and that basically you specify the parameters in a description.py file, and then you call this script and give it a directory that has a description.py in it. It uses the parameters from that file to create the model. That file also includes some other information about where to find the data. And it runs the model and then saves the results to a file, usually a file. It's pluggable in the description.py. You can specify the output, but we generally, when we're experimenting, just write it out to a file to look at afterwards. So here, here I'm going to run this with the same example, hot gym. So it's the same example I was using before. I don't know why this is. But rather than creating the CLA model myself, sorry, just trying to get this all on the screen. Rather than creating the model myself, I'm using the existing client and just specifying the parameters and where to get the data from. The output to the terminal here is not really that important. For the purposes of our talk, it's basically just periodically printing out the metrics as it goes, so you can kind of follow the progress. In this case, it's not a very big data set. I think I'm only feeding like 1,000 records through or something, so it runs pretty fast. And when that runs, it outputs this file in this inferences directory. In the directory that I ran it, creates this inferences directory that has a CSV file. And that CSV file is basically the input data with a few columns added on that have essentially what was in that inferences section of the model results when I ran a record into the CLA model and got the result back out. And I was looking at the inferences section, which has the multi-step predictions and the anomaly score. Those get added on as additional columns. And this is pretty difficult to see here with it so narrow. But I'll just point out in this first example, you can see this is the record that was fed in. And then initially, before I got the predictions, you here, this is the best prediction. So it's saying it predicts a value of 21 with a likelihood of 1 because it's only seen one record so far. But and that is you don't have to write the whole Python script yourself. This client is already written. You just have to create a file in this in the format that it understands, which is the description.py file, which I'll show you. And this looks very similar to the model params that I showed you before. It's actually pretty much the same exact thing. So config here is what I was calling model params when I was creating the CLA model myself. And then there's a few things at the end of this file, in addition to the model params, that control things like where to put the results. In this case, I'm just specifying a file somewhere. And there's also the ability to specify what metrics you want it to compute. I'm not going to go too much into detail. What I would say is look at this example and start with that. If you want to use this tool on your own data, basically start with this and then just adjust the encoders to match your data and then run it, and then you can tweak the parameters.
There's also pages on our wiki about running swarms, about the swarming algorithm, and it links to a video on running swarms, a presentation given by Ron Marionetti about this as well.
That's a great point. What if you want to do swarming? Okay, so that's actually the last thing I have to talk about, and it's going to go really quick. So I'm just about done. You might wonder why you would use this description.py. It seems kind of kludgy rather than just creating the CLI model, and it's basically a more constrained version. You don't get to arbitrarily program what to do. You have to just specify the parameters, and then the OPF run experiment script does what it will. But the advantage of this is that because we've structured the data, we can run a swarm on it, and the swarm tool basically allows you to specify which of those parameters you want to permute over and what range do you want to try. And then it will run a bunch of different models with different combinations of parameters and figure out which ones get the best results. So this is the swarm script is just in the NuPIC repository in bin run swarm. And then I'm going to pass the same path that I passed for OPF run experiment, but I'm going to point to the permutations file, which kind of mirrors the description.py, but it just specifies which of those fields we want to permute over, and I'll show that in a second. But first, let me run this. Again, there's going to be a lot of output here. It's just kind of, so as it's running, you can kind of like see where it is. For most cases, you probably don't need to understand exactly what all this means. When this finishes, it's going to write a directory that's going to have the description.py file from the best model from all the models that I tried. So it's taking a base description.py that I ran before. It's changing some of the values, running a model with the new values, checking the results, and doing that a whole bunch of times, and keeping track of which one worked the best. Then at the end, it takes the one that worked the best and writes those parameters into a file. I should have started this a little bit sooner, but so when that's done, it's going to write this directory called model 0. Is that big? That's not big enough. Is that big enough? Can you guys see that? Okay. So inside this model 0 directory, it's going to have a description.py, and inside that file are just the differences between this file and the base description.py that it started with. So you can see at the bottom, it's doing this import base description and then updating the config with those values. So in the permutations.py script, we specify. I should have showed that first. Let me show that real quick. So when you do swarming, I mentioned you specify which fields you want to permute over. Again, I would recommend taking an existing example and then just adapting it to work with your data. But basically, there's these different classes that you create instances of for different types of values. So permute encoder is a permute object that understands encoders. So it's going to permute specifically over this floating point value for I think that's the radius. It's a little, yeah, it's the radius of the encoder. So this is a random distributed encoder. The radius is how big the buckets are, and the value of that can change a lot based on your data. So if your data has really large values, generally you're going to want a bigger radius, and if it has really small values, you're going to want a smaller radius. But fine-tuning that can have a pretty big impact because that can take out some of the noise to take some of the burden off the algorithms. But if it is too big, then you're gonna the buckets are gonna basically represent multiple values as the same thing that you might not want them to. So when the swarm runs, it looks for these permute objects in here and picks a value in the range, runs the algorithm, and then for each of those permute objects in the permutations.py file, when it picks that best model and writes out the description.py, it's going to write out the values that it had for each of those. So just as an example here for time of day, these values were specified as something that we wanted to permute over, and these are the values that it came up with as the best. So that's basically it for swarming. I can't really give too much information. It's going to depend a lot on your data set, but I'd recommend finding an existing example that's similar to your data set and then adapting it. And that's why you guys are all here, so you can try this out, and if you have any problems, you can talk to us about it. But I hope that makes sense. Did you have a question?
So real quick, so when you run the swarming, do you actually have to specify like what's the metric that it's trying to optimize? Is it actually doing an optimization, or is it just combinatorially expanding all your parameters and then picks whatever has the highest? Like, do you have to configure all that and do all that, or is that built into your tool?
That's a good question. So part of the OPF is this notion of metrics, and in the description.py file, you can specify what metrics you want. I showed that briefly at one point, but didn't really go into details. It's going to take whichever one you specify first, whichever metric you specify first, and use that as the metric that determines which model is considered best. So when it runs the models, the output gets fed into the metric, and then that metric will give you a value, which is, the lower the value, the lower the error, and the better the model. So it picks the one with the lowest error. There's one kind of tricky thing about those. You can specify a window for them. So if you have 10,000 records and you specify the window as 1,000, it's going to just compute that metric over a moving window of 1,000 records. So when you run the swarm, it's going to take the last 1,000 records, and the metric over those records is what's going to be used to determine if it's better than another model. So keep that in mind.
Hold on.
Kind of a newbie question, but I'm not sure that I have the proper understanding of the term model that you've been using. My understanding is instantiation of the CLA in a particular configuration. Would that be a good way of describing the term model?
Yeah, I think that matches my understanding. But like I was saying, the OPF has this kind of pluggable architecture, so you could create a different type of model, like an n-gram model, and that would, well, when I say, I guess you're saying instantiation. So when I say model, I guess I use it to mean either an instantiation or just the algorithm, like
well, maybe one
implementation of the
good way
algorithm.
of getting to the point would be, what would be the difference between two models? Like what would
Yeah,
be?
I guess I have it
One might
overloaded,
have
so.
a temporal pooler and one might not utilize a temporal pooler. Would those be two different models, or?
Yeah, I guess I use it two different ways. One way I use it is talking about the implementations of the algorithm. So the CLA is a different model from like an n-gram model. That's the abstract level. But then I would also use it to say an instantiation of the CLA without a temporal pooler versus an instantiation with are two different models.
Okay.
They're the same type of model, I guess.
Okay. I'm just used to thinking of models as like a database,
admittedly,
data format or something.
Yeah, admittedly, I'm overloading the term, so.
Okay, I just want to make sure I was
Yeah.
correct on the term. I think mine matches yours. Thanks.
Okay.
I'm still a little confused about how the classifier connects to computing the anomaly score. Is there some sort of metric that is actually used for the classification function that helps contribute towards that score?
No. When you're computing the anomaly score, it does not use the classifier at all. And you can actually throw away the classifier and not use it at all and still get anomaly scores out. It's only needed to get predictions. And if you want to swarm on an anomaly model, if you have an anomaly problem, you may still want to do swarming. And in order to do swarming, you have to have a classifier because you need the predictions to evaluate which model is better.
Okay, so the classifier is used in swarming or is used in prediction? Or
Correct. Both.
Both.
Yes. Yes, in swarming, it uses the predictions to determine which model is best.
Any other questions?
This is it for my presentation, so if you're waiting for anything else, I'm sorry.
Well, just one more clarification. I was having some trouble distinguishing between the encoder and the spatial pooler because it seems like they were performing similar functions, but is it right to say that the spatial pooler would take multiple variables which have been encoded and create the kind of group SDR from those multiple variables?
So the encoder takes a value and turns it into ones and zeros, and generally encoders don't learn at all. So for a given input, the output from the encoder will always be the same, where the spatial pooler adjusts the weights of the connections to the input bits for each column. So over time, as those change, the output will be for a given input will be different. Does that make sense?
Yeah, that's clear. Thanks.
And the spatial pooler also requires an array of ones and zeros as input. So if you are starting out with the value 5 you have to first put it through the encoder to get ones and zeros. The output of that encoder will always be the same for the value 5. And then when you put it into the spatial pool, or the output of that, you don't really know what it's going to be. It's going to be the spatial pooler's invariant representation of that value, which may change over time.
Okay, cool, thanks.
Thank you, Scott Purdy.